Hi. In this video, we're going to continue our discussion of linear systems, moving away from the qualitative discussion that we had in the first video, thinking about what do linear systems represent geometrically in both the row picture as a set of lines or a set of planes or a set of hyperplanes, or in the column picture as an attempt to write a linear combination of vectors to yield a right-hand side vector, and shift our attention instead into how we solve linear systems using a technique called Gaussian elimination. Gaussian elimination is an algorithm or a set of steps that we can apply to any system of linear equations to get a solution if one exists, and in fact also to identify the cases where a solution does not exist. It involves two key steps that we're going to expand on in a moment: forward elimination and back substitution. Both of these components of Gaussian elimination make use of the idea, the concept, that we can eliminate a variable from an equation by subtracting a scalar multiple of another equation from the system from the equation we'd like to eliminate a variable from. And by applying a set of rules that subtract or add scalar multiples of one equation from another in a well-defined order, we can systematically reduce the system to isolate the variables in a way that we can easily evaluate what they must be in a solution. The first step is forward elimination, and we'll be moving on to an example in a moment to really highlight how this works. But first of all, to sort of schematically or sort of qualitatively describe the process. We have an outline here. Forward elimination always works from top to bottom and from left to right. We begin with the first equation, the topmost equation in the system, and we focus our attention on the leftmost variable in that equation. We use that first entry in the first equation as something that we call a pivot to eliminate or zero out all of the entries below it. After doing that, we have only one equation that has that first variable. We then move to the second question, moving down a level, and over to the right one position, and look at the second variable. Again, we use that entry from the second equation as a pivot to eliminate the entries below, move down and to the right, and repeat until we reach the bottom. And at that point, we have a form of our system of equations that is known as an upper triangular form and has all of the information in it that our original system did. So let's work through an example to really highlight how this works. In all of the slides moving forward, I'll leave the qualitative description of forward elimination here on the right, and we'll go through the work for the particular system on the left. The original system we have here, let's work through this process top to bottom, left to right. The very first thing we do is we're going to identify the pivot in the first equation, the first entry in the first equation. And what we would like to be able to do is to use this as a mechanism, to use this first equation to remove the terms, this first term, from the second and third equations. And what we're going to need to do to be able to do that is, since the second equation has an x just as the first, if we take equation 2 minus equation 1, we would get that. the equation 3 has a 2x, so in order to get a 0, we would have to do equation 3 minus 2 times equation 1 to zero that out. And that's exactly what we have highlighted here. We're going to subtract the first row from the second and subtract twice the first row from the third. X minus x gives us a 0, just as we would like. 3y minus y gives us 2y. Z minus negative z gives us 2z. 1 minus 1 gives us 0. Moving on to the third equation, we're going to subtract again twice the second row, so 2x minus 2x again gives us our 0 here. 3y minus 2y gives us y. 3z minus negative 2z, 5z, and negative 2 minus 2 gives us negative 4. The first step is complete, and what are we left with? We're left with a column that contains a single value at the top and all zeros below it. We've eliminated x from everything except from the first position. We then move on, and in the next step, we repeat the process after shifting our attention down a row and over to the right. From this point on, in forward elimination, we really completely ignore the first equation. The first equation stays completely unchanged, as in the second, after remaining processes. Everything else we're going to look at here in this second section. The leading entry in the second equation is going to be our next pivot, and we want to use this to eliminate the entry below. What are we going to need to be able to do that? Well, we have a y in the third row and a 2y in the second. The subtraction we're going to need to do is the third row minus 2 times the second row. Subtract, sorry, not 2 times, half times the second row to get this down to a y. Subtract half the second row from the third. And that's exactly what we do here. Y minus half of 2y is, of course, 0. This gives us our 0 in this position. 5z minus half of 2z, 4z. Negative 4 minus 0 leaves us a negative 4. Now we have successfully done the same thing that we did with the first column. The first column still has a single position with x, and the rest are zeroed out. And what we've now done is we've zeroed out an additional piece here. Our pivot is in the second row is the first entry of that second equation. Actually, at this point, we have now reached the end, because if we shift our attention down, then we have nowhere more to go, right? Shifting our attention downward by one row and one column leaves us with our last equation. We're done. If we focus on what this equation looks like, we see that this last row has a single variable. We can directly from this compute z. The second to last has 2 variables. The third to last, or the first, has all 3. This is what we mean by an upper triangular form for a system of equations, because if we think about at least the left-hand side of this system, we can enclose it in a triangle. like this, rather than the rectangle of arrays that we started, of entries that we started out with. Right? Now, this sort of system is very easy to solve because the last entry has a single variable well defined. We can solve for this value, then plug that value into the equations above. That will leave us only with a y in the second equation. We can solve, plug it in, solve, and so on. Upper triangular matrices are easy to solve. Although they're easy to solve, we can still regularize the approach, and that approach is known as back substitution. In the same way that with forward elimination, we started at the top with the first equation and shifted our attention left to right, moving through the system as we move downward. Back substitution starts at the bottom, moves bottom to top, and our attention shifts from right to left. We start with the last equation, and the upper triangular form gives us the value of the last variable. Right? The last equation, looking at the last variable. We then substitute this value in the equations above. We then move up to the second to last equation, move left to the second to last variable, solve for that, substitute, and repeat, moving up a row and to the left until we have our complete solution. Again, this is easiest to see continuing on our example, so let's take a look at this. Our triangular system after forward elimination is given here, and once again, as with forward elimination, I have the qualitative description of back substitution on the left here, or sorry, on the right there. First step is to solve for z. Our last equation has a single variable, 4z equals -4. Clearly, z must be -1. We then take this value of z equals -1 and plug it in to both positions in the second and first equation that have a z. Negative z, if z is -1, becomes +1. 2z, if z is -1, becomes -2. Right? Our new system is here. We have solved for z and substituted. We're ready to move forward. Again, we shift our attention up and to the right, or sorry, to the left, up to the second equation. This equation after substitution has a single variable left, the variable to the left of z, y. Okay? Now we again solve for y. 2y minus 2 equals 0 tells us that y must be +1. After evaluating y equals +1, we substitute the remaining value of y in the first equation to get the first equation now in this form. We're now ready to solve, again shifting our attention up to the first row. The first row is now has a single variable in it. That single variable is leftward of the variable that we just found. Solve for x. X plus 1 equals 1 means that x must be -1. At this point, we have a complete solution. Our system now simply tells us x is -1, y is +1, z is -1. We could leave it in this form, but we often represent solutions to systems like this, thinking of them as ordered triples, as vectors in perhaps in a space. And so we might write this as the solution being the ordered triple of x, y, z equals -1, 1, and -1. Okay. This approach works for any system with a few caveats. In many, many cases, the procedure of Gaussian elimination that I just outlined proceeds very smoothly, giving a unique final solution. but we know from our discussion in an earlier video that some linear systems don't have a solution. We know that some linear systems have many solutions. What happens with Gaussian elimination in those contexts? Are there cases where there is a solution and but Gaussian elimination may give failure or a hiccup? Let's explore some of the things that can happen to potentially interfere. And what we'll actually find is that there's workarounds for all of these. So let's take another system, and we're going to work through in exactly the same way. Top to bottom, left to right. Focus on the first equation of the first variable of the first equation and use this as a pivot to eliminate downward. Subtract the first row from the second and twice the first row from the third. These have the same coefficients as the last system, so the first step is the same. X minus x gives 0. 2y minus y gives y. 2z minus z gives 3z. 1 minus 0 gives 1. 2x minus 2x gives 0. 3y minus 2y gives y. Z minus 2z gives, or minus negative 2z gives plus 3z. Negative 2 minus 0 gives negative 2. Already here we see a potential concern. If we look at these last two equations, we see they have identical left-hand sides, but different right-hand sides. Something that tells us we can't have a solution. These are parallel planes. We might have noticed that and realized there was no solution. If we didn't, if we simply continued moving forward to apply Gaussian elimination as we normally would, we shift down and to the right, moving to the second equation, focus our attention at the first position of that second equation, and use this as a pivot to eliminate below. We're going to do this by subtracting the second row from the third. Y minus y gives 0. 3z minus z gives 0. Negative 2 minus 1 gives negative 3. The equation that we end up with is obviously a false statement. 0 equals 3. This is our indication that we don't have a solution. We had parallel planes from two equations that had the same left-hand side but a different right-hand side. We tried to subtract them. The left-hand side's perfectly canceled, but the offset, the right-hand side didn't, and we get an inconsistency. We say this system is inconsistent. It does not have a solution. What we have seen here generally translates to any system. If during forward elimination we get an equation that has a 0 on the left-hand side, but a non-zero entry on the right, the system has no solution. We can catch this earlier in some cases. If forward elimination ever results in two equations that have the same left-hand sides but different right-hand sides, the system has no solution. If you reach either of these two states, you have identified that the system has no solution, you can stop the process of Gaussian elimination. There is no point in moving forward because there is not a solution to the system. All right. There's a case of no solution. What about a case with many solutions? I've constructed such an example here. Let's work through Gaussian elimination in the normal way. We start focusing our attention in the first equation, the first variable. We want to use this as a pivot to eliminate below. In this case, to do that, we need to subtract twice the first row from the second and subtract the first row itself from the first. 2x minus 2x will give us the 0 we wanted. Y minus 2y will give negative y. Z minus negative 2z, 3z, 1 minus 0 gives us 1. X minus x gives us 0. Important to note in this kind of equation that we have a 0 here. The missing y is simply 0 times y. 0 minus y gives us negative y. 2z minus negative z, 3z, 1 minus 0 gives us 1. Here, our last two rows still have identical left-hand sides, but also have identical right-hand sides. This tells us something's going on, but is not a reason to stop. There is nothing inconsistent about this. If we follow through using normal Gaussian elimination, shift our attention down and to the right, first variable of the second equation used as a pivot to eliminate below. This will be achieved by subtracting the second row from the third. Negative y minus negative y gives 0. 3z minus 3z gives 0. 1 minus 1 gives 0. We get a final result of 0 minus 0, or 0 plus 0 equals 0. This is true. There is nothing incorrect. We have not reached an inconsistency. We should not stop. But this is trivially so. It doesn't have any information in it, and this will have consequences, or may have consequences, for what we see down the road. Right? If we try to now continue Gaussian elimination and focus our attention downward, we shift down, and we see that this last row doesn't have any information in it. It's the trivial statement that 0 equals 0. We simply ignore it from our consideration. We can completely, really, just stop writing it completely. In that case, we have nowhere more to go. We have reached our last equation. We can't continue moving downward. We are in our upper triangular form. Right? All right. So, given that, the next thing we should do is to do back substitution. But if we look at this second to last equation, which is now last after deleting this 0 equals 0 equation, we have two variables. We have a y and a z. We can't simply solve for one variable as a number, but we can solve for one variable in terms of the other. We are going to highlight which one is the pivot. The pivot is the first non-zero term, and we want to solve for that pivot for y in terms of the variables that are left, which we call free variables. Solve for y in terms of z. Negative y plus 3z equals 1 means that negative y is 1 minus 3z, or y is 3z minus 1. After solving for y in terms of z, we can plug that back in, substitute that into the first equation to eliminate y from that piece. So we substitute y for 3z minus 1. Moving forward, we now shift our attention up to the first equation, over to the leading term, the pivot variable in that equation, which is this x. And we see the only thing we have left in here are z's, which we've already said we know is a free variable. Solve for the pivot in terms of the free variables. Solve for x in terms of z. X plus 3z minus 1 minus z, sorry, there should be a plus sign in here, minus z equals 0, means that x must be 1 minus 2z. At this point, we have solutions for both x and y in terms of z. What about z? We've mentioned that it's a free variable. What does that really mean? It means that z can take on any value. Z can be any real number, And regardless of what it is, we will be able to find an x and a y in terms of that z that satisfy the system of equations. We could leave it at that. We could leave our answer in this form. Y equals 1 minus 2z, sorry, x equals 1 minus 2z, y equals 3z minus 1. Z can be any number. Very often we try to write this again as an ordered triple. And in order to eliminate any confusion about x, y, and z as variables from our original model, as opposed to a well-defined solution that has a free parameter, we recast that free variable with a new variable, so say z equals t, and then write x, y, z is 1 minus 2t, 3t minus 1, and t, where t can take on any real number. We call this a parametric form of the solution. This is how we deal with systems with many equations. If forward elimination results in an equation that has a 0 on the left-hand side and the right, we ignore it. 0 equals 0 doesn't mean anything. We simply proceed with the process. If the upper triangular form, when we're finished, has free variables, that is, we look at where the pivots are, and now there's some variables that aren't a pivot, then we know that the system has infinite solutions, and we can solve for those pivot variables in terms of the free variables and write a parametric solution. All right, so we've covered the case of a unique solution, we've covered the case of no solution, we've covered the case of many solutions. What else can go on? Well, here I want to highlight not a problem as much as a small hiccup that can arise under certain circumstances. Another system, related, a lot of shared features as the other ones, but a little bit different. Again, standard forward elimination. We start at the top left. We want to use this first variable in the first equation to eliminate below. Since everything here has the same coefficient, we simply subtract the first row from both the second and from the third. X minus x is 0. Y minus y is also 0. Look at that. Z minus negative z is 2z, and 2 minus 1 is 1. For the third row, x minus x is 0, 2y minus y is y, and 2z minus negative z is 3z. 1 minus 1 equals 0 for the right-hand side. We might notice immediately that this second row is missing the pivot entry. If we try to take the standard approach and move down and to the left, we reach this problem where we do not have an entry in this first position. It's missing. We have an entry below it, but we don't have one there. How can we possibly use a missing entry as a pivot to eliminate? Comes down to really a divide by 0 problem. We can't. Are we stuck? No. These are simply equations. Remember the geometric picture of what does a system mean? The row picture says that each of these are planes in 3 dimensions, and the solution is their intersection. It doesn't matter the order we write them. We could write the first one and then the second one and the third one, or the third and the second and the first, or the first and the third, the second. It's all the same collection of planes. So we can swap rows such that elimination can proceed properly. We're going to take these 2 equations and we're just going to exchange them. And that's exactly what we have here. Swap rows 2 and 3 so that we're in a better position. Right? Now we shift after doing that row swap, we shift our attention back to this equation here, and we actually notice that the problem that we had that led to the row swap also means that we don't have anything to do in this next step. We already have a 0 below this pivot in the second equation, so we can shift our attention down and to the left. Down and to the left gives us only one equation. We're finished. We're in our upper triangular form, and we can proceed with back substitution. Right? Just to give a little bit of extra practice on how we do this, focus on our last equation, bottom row, last variable, solve. 2z equals 1 means z equals half. Take this answer and substitute it in to the places where there is z in the rows above. Negative z is negative half, 3z is 3 halves. We then shift our attention upward to the next equation and focus on the pivot, which is to the left. Again, solve for that value. Y plus 3 halves equals 0 means y must equal negative 3 halves. Once we've done that, we substitute for y in the first equation. Y becomes negative 3 halves. Shifting our attention upwards again. Remember, back substitution moves bottom to top. Our attention shifts from right to left. Solve for this pivot in the first row. X minus 3 halves minus half, or x minus 2 equals 1, means x must be equal 3. We now have a unique solution that we can directly read off, right as the ordered triple, x, y, z is 3, negative 3 halves, and half. Right? If during forward elimination the pivot variable is missing from the row we need, we simply swap it with a lower row than that does contain it. The need to swap rows does not tell us anything about the set of solutions. We can have a well-defined solution with row swaps involved. In some cases, we might swap rows and later on discover there's no solution or many solutions or so on. All right. Let's take another example of something that can happen. Another system, we're going to work through this exactly the same way. Start with the first variable in the first position, use it as a pivot to eliminate below. Row 2 minus row 1 and row 3 minus row 1. X minus x is 0, y minus y is 0. Again, we get 2 zeros here. Z minus negative z plus z, 0 minus 2, negative 2. For the third row, x minus x is 0, y minus y is also 0. Negative 2z minus negative z is negative z. 3 minus 2 is 1. Here, we see that the second row is missing the pivot, but so is the third. Right? If we try to shift our attention down and to the right, we don't have a pivot here. But there's nothing to exchange with. It doesn't matter there's nothing to exchange with because there's no information in this column. We simply skip that column. We have no pivot here. There's no equation that has y of a pivot. This tells us that y is a free variable. We continue. We don't get to move down in a row because we didn't actually use a pivot, but we shift our attention over to the right. Okay. We now use this entry, the first non-zero entry in the second row as a pivot, to eliminate below. How do we do this? We add half of the second row to the third. Negative z plus half 2z gives us 0. 1 plus half of negative 2 is 0. And we see actually we also get here a 0 equals 0. Not a problem. When we get a 0, 0, we just ignore it. After forward elimination, this is the system we have. It's our upper triangular form. We move the same strategy for back substitution. start with the last entry, the last row. The last row, in this case, has a single variable that we can directly solve for. 2z equals -2 means z must be -1. We then substitute -z if z is -1 becomes -1. Shift our attention upward and to the left. Sorry, let's move. Apologies, I forgot this is a poorly written expression because I didn't sort of copy this over properly. This should simply say is +1, and this should say z is -1. Right? After that first step, we have our pivot x. We have a variable remaining. We've already identified y is a free variable. So how do we solve for x? We solve for x in terms of that free variable y. Solve for the pivot in terms of the free variables. If x plus y plus 1 equals 2, then x equals y, 1 minus y. We have our solution. Once again, we have our solution in terms of our free variable y. Note that not every variable has to have that free variable in it. Z is well defined as a single value, but x has this flexibility of the free variable. In the same way, we define our free variable to be a parameter. I like to use t, s, values in that sort of symbols in that area of the alphabet typically. And we have our final solution, x, y, z, 1 minus t, t, and -1, where y can be anything. If during forward elimination the pivot variable is missing from the row that we need it in, as well as from all of the lower rows, we identify this as a free variable. If we have a free variable, the system has multiple solutions, infinite solutions. That doesn't mean we stop. We simply shift over to the next pivot, continue the process of forward elimination, then apply back substitution where we solve for the pivot variables in terms of the free variables, and then write our parametric solution. Right? So we now can sort of have a little bit of a summary. Gaussian elimination, we've seen, is a robust set of rules that we can apply systematically to any system of equations. And we have ways of dealing with essentially every special case that can arise. If the system had a unique solution, forward elimination followed by back substitution will give that solution. Occasionally, we may need to swap rows to deal with a temporary hiccup of a missing pivot. If there is no solution, a row with a 0 left-hand side and a non-zero right-hand side will appear during forward elimination. This will always happen if there is no solution, barring arithmetic errors. Right? If this happens, we know to stop. If there are many solutions, at least one variable won't be a pivot. It won't be the leading entry in one of the equations in the upper triangular form. We don't stop. We still apply back substitution, giving a solution for the pivots in terms of the free variables. We can write that then as a general solution in parametric form. All right. There will be an accompanying video where we go through more examples of Gaussian elimination on systems of equations with all the special circumstances that can arise. There is also a next content lecture that focuses on still using Gaussian elimination, but simplifying the way we write this using the language of matrices. That can greatly simplify the amount of writing we need to do, simplify the thought process, and also provides a tie-in to some very, very important ideas in linear algebra. Thank you, and goodbye.